Hi, my name is David Sobral, and this is a short review into the nature and evolution of H-alpha selected emission line galaxies up to redshift 2.5, and also a little bit into what the future may bring, especially by exploring James Webb. First of all, let me thank the organizers of this meeting within the meeting, Sajita Malhotra, James Rhodes, and also Ali Kostolan. Now, in this short review, I'll be focusing on this period, the last 11 billion years, essentially since the peak formation or the peak of the star formation history until cosmic dusk or the present, and also focusing on H-alpha selected galaxies. So I'll talk a little bit about how we search for these line emitters, and first of all, also why H-alpha is so interesting and important. Also going to point out that we've learned about the nature of these H-alpha emitters, about how they evolve essentially from 11 billion years ago until today. And also at the end, I will point out how James Webb will really revolutionize our view of the very early universe into the epoch of ionization by allowing the first H-alpha studies, both undertaken blindly, but also by following up, for example, UV selected galaxies, and then getting their spectra, which will contain H-alpha. An important question you could ask is, why would we care about H-alpha, this recombination line that will come mostly from H2 regions? The reason why we want to conduct H-alpha surveys and use H-alpha is because it is an excellent star formation rate indicator. It actually comes out in rest frame red, so it's not as sensitive to dust as we shall see, and it will originate in ionized hydrogen clouds or H2 regions, essentially around very massive stars, O and B stars, and these stars are very, very short-lived. And this means that when you see H-alpha in an H2 region, those stars are still there, so they haven't gone supernova, and this also makes H-alpha a very instantaneous star formation rate indicator. The other important aspect to consider is that current instrumentation is actually sensitive enough to look for H-alpha as it redshifts into the reddest wavelengths into the near infrared up to very large cosmological distances until it actually redshifts out of the infrared band. It's of course very important to consider that even though when we think about H-alpha, we think of it as a star formation rate indicator, this is only true if we're actually looking at H2 regions. And for very distant sources, it may not be obvious what is powering H-alpha, and it is important to actually mind the presence of AGN. And AGN can also lead to a lot of H-alpha emission, and I'll point out towards the end of this short review. Apart from being a very instantaneous star formation rate indicator, H-alpha is really powerful because it will go through any neutral hydrogen, and like lemon alpha that you can see here in the illustration, that will scatter out of the line of sight. But also it will go through dust in a relatively easy way. You will still get attenuated by some amount, and I'll come back to that towards the end of this review, but it will not be attenuated like the UV. And I'll try to show you that even when you have regions like this, where a lot of dust is present, H-alpha can still go through. It will be significantly attenuated, so you do need the far infrared to get the full picture, but you can use H-alpha as a way to select star-forming galaxies and star formation activity, unlike the UV that can be completely gone. So in this talk, I will be focusing on H-alpha and a powerful way to select star-forming galaxies, to study star-forming galaxies. But it is important to point out that, as anything in extragalactic astrophysics, you cannot restrict yourself to a single indicator, and you only really get the full picture once you combine all the indicators. In this case, for example, looking at the UV and the far infrared, and ideally also combining with rest frame UV lines. By now, hopefully you're convinced that H-alpha surveys are really worth doing. And obviously you're not the only one. A lot of people have been conducting surveys. The way you do that is obviously by conducting emission line surveys. They are ideally blind so that you don't have to pre-select, but a lot of surveys have relied on some pre-selection, and then you'd put a fiber or a slit. But nowadays, surveys that rely on integral field units are very common. Spectacular instruments like MUSE Many surveys have used the GRISM capabilities of Hubble, like 3D HST, while many other surveys have explored narrowbands, like one pictured here, and you can put these filters in front of very wide field cameras to conduct very, very wide surveys. And you can build many of these filters to slice the universe in multiple redshift slices. So these are some of the surveys that have been conducted, some of them going very wide, some of them going very deep, and also some super wide surveys are ongoing, like J+, and that are only really just starting, like JPAS. A very important thing to point out is that even though there's sort of two main approaches to conducting these surveys, you can typically go very deep, but on a very narrow field of view, or you go very wide, but you don't go as deep. It's only by combining these two approaches that we can really get the full picture. We do require both the faint end and the bright end to make significant progress. Once you conduct your favorite survey, be it with the GRISM, with an IFU, with narrowband, and you select your H-alpha emitters, and I'll not go into the details, but you can see all the references. They all discuss how you go from taking your data to getting a final sample of H-alpha emitters. Once you know that they're there, you know their redshift, you know the volume that you've covered, and you know their luminosity. And essentially the first thing you do if you want to conduct a census for H-alpha emitters is you look in the volume, and then you count the number of H-alpha emitters with a given luminosity. And this is what is shown here. This is a recent plot by Ali Kosovan with the Lagos survey at redshift 0.5. And a lot of surveys have been conducted. So this is sort of the limit of what you can do in the optical. And typically what you really want to do is not just determine the H-alpha luminosity function at a specific redshift, you want to do it across redshifts. So instead of just using a single narrowband filter, you can build multiple ones all the way up to the K-band. If you do that, you can determine something like this and actually unveiled the evolution of the H-alpha luminosity function all the way from the local universe at redshift 0 to redshift 2.2. The main thing to take away from this is that there's very strong positive evolution in L star, or the typical H-alpha luminosity, but the faint end slope essentially remains very, very steep across cosmic time and does not appear to be changing, at least with redshift, although there are some environmental dependencies. Obviously, just obtaining a census of H-alpha emitters is not really telling you a lot about the physics or how the universe is evolving. And the next step will be to transform H-alpha luminosities into star formation rates. You typically need to know something about dust and how it is affecting H-alpha emitters, and I'll come back to this later. But if you make some reasonable assumptions, what you can do is transform the integral of the H-alpha luminosity function at a specific redshift into a star formation rate density. And that allows you to actually obtain the star formation history of the universe, or the evolution of the star formation rate density. Now, traditionally, the first measurements were all based on the UV. And one of the big problems about basing on the UV is that it's very, very affected by dust extinction. So not only can you underestimate the real star formation rate of a galaxy, you can just miss entire populations. However, over the last 10 years, we've finally been able to obtain a fully consistent star formation rate density evolution, or the star formation history of the universe, fully based on H-alpha. And the limit now is really around redshift 2.5, where H-alpha will redshift into the mid-infrared, and it becomes impossible to observe from the ground. But James Webb, fingers crossed, will be launched soon, and it will really revolutionize our view of the star formation history at the highest redshifts. And it's important to stress that currently at the highest redshifts, almost all measurements are based on the UV. There's some pioneering work using other lines that depend on metallicity, such as O2 by Ali Kosovan, but also some ALMA and radio results. Especially at the highest redshifts, the uncertainties really are quite large. And extending H-alpha surveys there will make a big, big difference. We can nonetheless do way more with H-alpha emitters than simply obtaining the star formation history. And in an ideal world, we'll be able to split this in, for example, environment and stellar mass, and many studies have started doing that. And one of the things that we've learned over the past few years is that Age alpha are main sequence galaxies. So they will follow the relation between star formation rate and stellar mass that's been established with other indicators as well. But something really interesting that has come out across redshift over the last 11 billion years is that if you're an Age alpha emitter, it doesn't matter whether you're forming stars in a field or in a cluster, your main sequence relation will essentially be the same. And this means that if you're an Age alpha emitter forming stars, you'll be forming stars at the rate that's essentially dependent on your stellar mass, regardless of where you are forming stars. However, if you actually survey for Age alpha emitters in clusters and groups and fields, and you determine the Age alpha luminosity function, you notice that the environment seems to be affecting the faint end slope. In very poor fields, it is very steep, as you can see on my right. And as you move to groups and clusters, the faint end slope becomes shallower and shallower. And this needs to be confirmed across redshift. So this is a specific result, redshift 0.84. It needs to be extended, and also it needs to be identified at which redshifts do these environmental effects actually take place. Another very interesting result that's coming out from a lot of surveys, including looking at 24 micron to Age alpha ratio, but also determine Balmer decrements like this study, is that Age alpha emitters, even though they seem to have the same star formation rate for a given mass, it looks like they are typically dustier if they're forming stars in a cluster versus forming stars in the field. And that's already taking into account the mass. And we'll go back to the fact that stellar mass is the primary predictor in terms of the dust properties of star-forming galaxies. But once you control for mass, the environment seems to be doing something. And this may be connected with starvation and more recycling happening on star-forming galaxies that still are forming stars and clusters. And that may also explain why, at least in merging clusters, Age alpha emitters seem to be more metal-rich for a fixed mass. Another very interesting result that's coming out from large surveys specifically targeting clusters, merging clusters and relaxed clusters, and determining, for example, the Age alpha luminosity function for those, is that there's a clear excess of Age alpha emitters in merging clusters compared to relaxed clusters. This is work that Andrea Stroh has been leading for a few years, and she also has this amazing spectroscopic follow-up that was just published this year that will definitely shed more light into why this is the case. And it may well be that the excess of Age alpha emitters is shockwave triggered. Essentially, the shockwaves are produced when the merging clusters actually merge. Selecting Age alpha emitters or any line emitters is really just the first step into sort of uncovering the physics and the evolution of star-forming galaxies and supermassive black holes. Fortunately, nowadays we do have access to the full spectral energy distribution of star-forming galaxies, including signatures that will come only from their supermassive black holes, like in the X-rays with Chandra, to high-resolution imaging with Hubble to reveal the young stellar populations in the terrestrial UV, all the way up to ALMA just on top of me that can uncover the dusts and also look at lines such as C2, and also into the radio, where we can look at radio synchrotron coming from both the AGN activity and star formation. The important message is really that only by combining all these traces can we get a full picture, but that Age alpha is arguably the best selector to provide you kind of a complete view of what's out there, and then you can explore the other facilities to unveil their nature further. One of the key results that has emerged over the last few years by exploring this multi-wavelength approach is that the sizes of Age alpha emitters and typical star-forming galaxies has risen over the last 11 billion years. The other important result coming out from studies like 3D-HST, and there's a very nice paper by Erica Nelson in 2012 showing this, is that Age alpha emission is always more extended than the UV counterpart, and that is also still more extended than the stellar mass. And together with many other papers, there's clear evidence for this inside-out growth of disks in the universe that can be seen for Age alpha star-forming galaxies. In general, Age alpha star-forming galaxies seem to be described by disks, being disk-dominated, most of them, but some of them are indeed mergers. One of the big revolutions of the last few years has been using Age alpha also as a way to explore the ionized gas in a resolved way. So this was first done with adaptive optics on a few objects with Symphony that really revealed that a lot of sources at high redshift seem to be disky or rotation dominated, but revealed really high dispersions. Over the last few years, with instruments like CAMOS, it really became possible to start doing samples, very large samples, with resolved H-alpha observations, including H-alpha selected. And what all these results show is that most star-forming galaxies on the main sequence are rotation dominated, but they have very high molecular gas fractions. And this is very likely the reason why they have such high dispersions. But apart from that, they seem to have relatively normal dark matter fractions. Resolved observations of H-alpha are already telling us a lot about the ionized gas, but it's really only when you combine observations, resolved ones at similar resolutions in the UV and in far infrared with ALMA that you really start to reveal the full picture. And you can really realize how biased the UV on itself can be. It will only show you the least obscured regions. H-alpha will actually tell you about the full distribution of star formation, but you may still miss it in absolute terms, and especially in regions like this that ALMA reveals that are incredibly dust obscured. In absolute terms, H-alpha will miss star formation, but you'll still be able to pick it up. And I think this is really, really crucial because it is showing in a resolved way why H-alpha is such a good star formation selector, in addition to being a really good star formation rate indicator. And it really provides a resolved view into previous results that have shown statistically that if you pick H-alpha emitters across redshifts all the way up to redshift 2.2, you really recover the full population of star-forming galaxies in one go. So not only do you detect the low mass, low dust extinction galaxies, but you also recover the dusty star-forming galaxies, including sub-millimeter galaxies, like this one would be picked with ALMA. H-alpha is a really good star-forming selector because H-alpha can go through the dust, but it's not completely immune to it. And we know that because typically H-alpha selected galaxies are affected by something like 1 magnitude of extinction. But one of the key results over the last few years that's really, really practical was to understand that if you know the mass of a galaxy, then statistically you can predict what is the typical dust extinction, even if you cannot measure it directly. There's, of course, a lot of scatter, but the important thing as well is that this relation is not evolving with redshift as far as we can tell. So this was first shown for H-alpha emitters. It's now been extended by many people to more general UV selected or far infrared selected galaxies. And the other important thing that came out of these studies is that even though there's a relation between dust extinction and H-alpha luminosity, that relation evolves with redshift. So it's not something very practical because you need to know the exact relation at a specific redshift. But that evolution means actually that at a fixed, if you fix the star formation rate, then higher Z galaxies are actually less dusty. So this means that a so-called lurg or U-lurg that you find at high redshift will not be as dusty as a U-lurg or lurg in the local universe. And this is a very useful result to interpret a lot of the observations. A lot of effort has also been put into measuring the typical equivalent widths of emission line galaxies, including H-alpha. And what studies have revealed is that the typical H-alpha equivalent width is going up with redshift, but at a fixed redshift, it goes up with decreasing stellar mass. So galaxies with lower stellar mass have higher equivalent widths. And the H-alpha equivalent width is very naturally connected with the production of ionizing radiation. You can interpret it with some caveats and with some assumptions about dust as a proxy for psi ion. Essentially, the ratio between the most massive stars, those that actually produce Lyman continuum photons, to those lower mass stars that still emit in the UV, but produce little to no Lyman continuum. And one of the big reasons why H-alpha and measuring H-alpha equivalent widths is important is because of this relation with stellar populations and its capability, especially in the future as we push these studies to the highest redshifts with James Webb, in terms of testing stellar populations. This is because different stellar populations predict different ionization efficiencies, and also what we may be seeing is a progression of typical galaxies becoming more metal poor, younger, and lower mass as we go up in redshift. What we've also been able to learn is that if you study typical age alpha selected star forming galaxies, even if you don't detect them in the X-rays or through any other indication that they contain an AGN, you can actually stack in the X-rays to measure their black hole accretion rates. And you can also do, as shown here, is compare the relative growth of supermassive black holes and the galaxies that host them for age alpha emitters over 11 billion years. And what the results show is that this ratio has been essentially constant over the last 11 billion years, and it's consistent with what has been measured locally. Of course, and as I told you in the beginning of this talk, sometimes when you pick age alpha emitters or any other line emitters, you may be picking them for the presence of an AGN. Over the last few years, it's become very clear that the probability of you picking one of these sources as an AGN depends strongly on the line flux or luminosity. This is true for age alpha emitters or for Lyman alpha emitters, but the extent to which you become fully AGN dominated is very different when you look at age alpha emitters, where you need to go to something like 30 times the typical luminosity before you become 100% AGN dominated, while if you look at Lyman alpha emitters, by the time you get to something like 2 to 3 times the typical luminosity, then you're essentially 100% dominated by AGN. And the big difference between the way that the AGN fraction rises with the typical luminosity is very likely to do with dust. And the fact that age alpha has a much easier time escaping some of the very, very dusty objects, while those very dusty, intrinsically luminous sources are not observed as very luminous when you look into the UV or Lyman alpha. Finally, the other thing that we've learned about age alpha emitters through large clustering studies is determining their dark matter halos that host them. If you want a very simple answer, typical age alpha emitters seem to reside in something like 10 to the 12 Milky Way kind of dark matter halos across 11 billion years. But there are very strong dependencies with line luminosity. And at any redshift, the higher the age alpha luminosity, the higher the dark matter halo that's hosting that age alpha emitter. In the sense that if you fix the dark matter halo and go up in redshift, you'll find galaxies forming higher and higher star formation rates. Another really interesting result is the fact that if you actually take into account the evolution of the age alpha luminosity function, and specifically the fact that the age alpha luminosity function evolves very strongly in L star, the typical luminosity, if you actually normalize age alpha luminosities by L star, you recover a single relation between the dark matter halo that hosts an age alpha emitter and its luminosity in relation to the typical luminosity at that redshift. I first proposed this in a paper back in 2010 when the samples were still small, and it's been really great to see further studies like Rachel Cochrane's and Ali Kostovan using much larger samples to really confirm that this is the case, and also extending these results to other line emitters. An important question that we can ask is, what are the progenitors and descendants of age alpha emitters and other line emitters? And the answer is, it depends. It depends on their line luminosity and redshift. So this means that many of the age alpha emitters that we're finding are progenitors of Milky Way-like galaxies. The more luminous ones are progenitors of some of the most massive galaxies in the early universe. And if you go and study the faintest age alpha emitters and the faintest line emitters, then they can be progenitors of even LMC-like galaxies. As I tried to point out, we've already learned a lot about age alpha emitters and line emitters in general, but there's much that we still don't know. And this is mostly because we don't really have the large enough samples covering all environments, and also our view at the highest redshift is still very biased towards UV-selected galaxies. Fortunately, I think the next few years will bring further revolutions, not only allowing us to understand more of what's happening at cosmic dusk, essentially from redshift 0 to 0.4, especially with surveys like JPAS that you can see on top, where about 8,000 square degrees will be surveyed with 56 narrowband filters, essentially allowing you to do a contiguous redshift survey, not only for age alpha emitters, but also for other line emitters, and actually use multiple filters to measure Balmer decrements, dust properties, and also to identify GN. This is basically a low resolution IFU survey of the local universe, covering all the way from voids to the densest clusters. And it's going to be very, very exciting. Furthermore, at cosmic noon, instruments like moons with 1,000 fibers on the VLT and James Webb and many other narrowband and GRISM surveys will certainly further advance our understanding and also obtain resolved observations to understand what's going on and the physics of sort of sub-kiloparsec star formation, and also the relation between AGN and supernova feedback at cosmic noon. And finally, perhaps one of the most exciting aspects that JWST will allow will be the first ever blind surveys for H-alpha emitters, both with narrowbands, medium bands, and also using the GRISM. And why do you want to conduct all these surveys from cosmic dawn to cosmic dusk? For a lot of reasons, because there's still a lot of open questions and a lot of physics that we don't know about. On one hand, I think one of the exciting things to pushing these surveys to high redshift will be to address the question about how much we're missing currently and how much we might miss if we purely rely on UV preselection to then put slits on galaxies. We might be missing an important population, and H-alpha surveys will be crucial to address that. On top of that, we'll be able to conduct some of the largest and deepest surveys. So this means that we'll be able to study both faint and bright sources across redshifts and understand differences in their physics and stellar populations. And this will really be crucial to test the current state-of-the-art stellar population models by also obtaining a lot of follow-up observations. This will allow us to answer questions about the production of ionizing photons, which is crucial also for reionization. And this will likely lead to a lot of discussions about the star formation calibration for H-alpha at high redshift, at high metallicities, and at the youngest ages. And finally, and especially towards the lower redshifts, but even at cosmic noon, with instruments like moons, and then with JPAS and many other surveys, we'll really be able to further unveil the role of nature and nurture across cosmic time with a single selection based on H-alpha. So this is it for this short review. I hope I've been able to show you why H-alpha is really a gold standard in terms of selecting star-forming galaxies and getting instantaneous star formation rates, but that you cannot ignore other tracers. And thus is still very important, and observations at long wavelengths are necessary, but also that even though we've learned a lot up to now, there's still a lot that we don't know. And I'm really looking forward to the future, especially with James Webb, but also with moons and JPAS to address some of the currently open questions. In case you have questions or want to discuss, please get in touch via email, Twitter, or any Slack space that you might find me.